To load a modern 3D video game, your computer springs into an expansive, orchestrated data migration the exact moment you press a key. A single immersive environment requires gigabytes of textures, complex logic pathways, and layered audio files to render accurately. But the brain of your computer, the central processing unit, or CPU, cannot ingest gigabytes of data at once. Its execution units can only process a microscopic fraction of that information at any exact nanosecond. This chart plots component storage capacity against access speed. If a fast CPU pulled instructions directly from a sluggish main drive, it would constantly wait, freezing the system. To bypass this, components form a memory hierarchy, a synchronized relay race. Data moves closer to the CPU through different systems, trading capacity for speed. The very first step of this relay happens before the operating system even loads. A tiny chip called read-only memory, or ROM, holds the permanent firmware instructions that wake up the motherboard and spark the entire process. Your computer's memory is an active, tiered ecosystem of specialized parts, constantly filtering and staging information to keep the processor fully fed. All your game files start their journey deep in cold storage, usually a solid-state drive or a traditional hard disk drive, which retain data even when the power is off. Inside a traditional hard disk drive, information is read by a mechanical arm swinging over physical, spinning magnetic platters. Relying on moving metal parts means fetching data takes milliseconds, an eternity in computing time. Solid-state drives, or SSDs, improve on this by using arrays of 3D NAND flash memory. These chips trap electrons to store data without any moving mechanical parts. But even though an SSD is significantly quicker, reading data still takes dozens of microseconds, which remains far too slow for a CPU core. So when you launch an application, gigabytes of that cold data migrate into the main memory, or RAM. This acts as the active staging ground. It holds the game's immediate environment in temporary memory cells that offer vastly higher bandwidth, allowing the system to access it in just nanoseconds. Simultaneously, complex textures and graphic models are routed specifically to the graphics card's VRAM. This dedicated memory handles rendering the visual environment independently, keeping the main CPU clear for logic and mathematical calculations. If you open too many demanding programs and your physical RAM becomes overwhelmed, the computer initiates an emergency triage response called virtual memory. It temporarily sections off a portion of your much slower storage drive to act as extra RAM, keeping the system from crashing. This staging process dictates the present reality of your machine. It physically holds exactly what is needed right now to maintain the illusion of an unbroken digital world. To execute the actual mechanics of the game, we now have to dive down from the motherboard into the microscopic architecture of the CPU die itself. This top-down schematic highlights the VIP lanes of the system. Cache memory. The processor has memory banks built directly into the silicon. The Level 3 cache is shared across the entire chip, while the faster Level 2 and Level 1 caches sit immediately next to specific individual processing cores, holding the exact instructions they are about to execute. Because cache memory is built from billions of dedicated transistors to maximize bandwidth, it is expensive to manufacture. Engineers must severely limit its capacity, shrinking the storage space down from gigabytes to mere megabytes to keep the processor affordable. From the cache, the relay race reaches its final destination, the CPU registers. Registers are the absolute fastest memory locations in the entire computer. They hold an incredibly tiny amount of data, measured only in individual bytes or kilobytes, but they return that information in a fraction of a single nanosecond. These locations sit directly next to the core's arithmetic logic units. They act as the immediate holding cells for the exact numbers being added, subtracted, or compared in any given clock cycle. By the time a sprawling 100-gigabyte game reaches the physical core of the processor, its expansive digital world has been successfully filtered down through the hierarchy into single microscopic equations, calculated in a single clock cycle. Because of this nanosecond perfect relay race across the different components, the execution units are never left waiting. That continuous, synchronized flow is what translates static code into a seamless, lag-free 120 frame per second experience on your monitor. This exact same architectural logic extends far beyond your home desktop. It scales upward to power the absolute cutting edge of global technology. Inside the vast data centers running modern artificial intelligence models, the physical servers rely on an identical memory hierarchy, scaled to industrial proportions to handle terabytes of active memory and petabytes of cold storage. Artificial intelligence introduces a specific computational bottleneck. To generate a single response, the system must maintain a constant influx of millions of input tokens and hundreds of billions of learned mathematical parameters directly into the AI processor. To accommodate this demand, engineers use high bandwidth memory, or HBM. This is the extreme evolution of near-processor memory, physically stacking multiple layers of memory dies vertically right next to the AI chip to achieve transfer speeds of over a terabyte per second. Computer memory functions as a synchronized circulatory system, making the physical realities of modern computing, from desktop gaming to generative AI, possible.